One of the coolest things about Newton's law of gravitation is that it allows us to actually find the mass of objects out in space, and all that's required is to observe the orbit of something that's going around that object. So just qualitatively, to remind you of the physics behind this, the Earth is moving in this circular path centered around the sun, and at any given moment is accelerating toward the center of curvature. That's the only way an object can move in a circular path with a constant velocity. So the Earth's orbit isn't literally circular, but is extremely close to being circular. So this is a good approximation. So the Earth accelerates toward the center of curvature, and the reason why is because it's being pulled toward the center of curvature by the force of gravity. And Newton's second law, or not Newton's second law, but law of gravitation, tells us how to calculate that, how hard two masses pull on each other when they're separated by a center-to-center distance of r. So I want to solve this problem in general first, and then we've got to do a lot of unit converting in order to get to the solution. So I'm just going to start with Newton's second law, and we're analyzing the Earth here. I'm going to call it a mass of m. And we're going to look at the net force on it, and there's only one force on it, so there's not much to do there. The net force on it is this force of gravity pulling to the center. So I have G, M, big M, that's the sun, M over R squared equals mass times acceleration for the Earth. Now I could put in V squared over R, but it's a lot easier to look at orbital period. So we can look at the formula for centripetal acceleration in terms of period, and that's a 4 pi squared r over t squared. And what you'll notice here is the mass of the Earth does not need to be known in order to get this done. And so astronomers do this all the time with finding masses of other planets, finding masses of other stars. You just have to observe something orbiting around it, and you can do this calculation. Okay, and then what we're after here is the mass of the sun. So M, big M. I'm going to multiply r squared on both sides, so I end up with 4 pi squared r cubed. And then I'm going to divide by g. And I've got an expression for the mass of the sun based only on the orbital radius for the Earth going around the sun. And I lost a t squared, so I better put it in. The orbital radius and the period. Okay. Now we get into our data. So we have the constant g written down, so we can put that in. And then r is called an astronomical unit, or AU. That's the average distance between the Earth and the sun. And it's given here in kilometers, and we're going to have to convert that to meters, and that's not so bad. We don't need to write any calculations down. I'll just tack on a factor of 1,000. So r is 1.496 times 10 to the 11 meters. And then t, we're going to have to actually do some work. Well, what's the period of rotation of the Earth around the sun? That's a year. So I'm going to have to do a unit conversion on a year. T equals 1 year. And we'll just be a little bit crude about this and just say 365 days. And 24 hours in a day. And 3,600 seconds in an hour. That's 60 minutes, 60 seconds each. Years cancel, days cancel, hours cancel, and I end up with my period written in seconds, which is a lot of seconds. So 365 times 24 times 3,600. I'm going to keep a lot of decimal points for now, I suppose. Gives me 3.1536 times 10 to the 7 seconds. And I went ahead and plugged all of those numbers in. It'd be interesting to look at the units here. I think it might be unwise to get into all the details, but if you wanted to check it, you would replace a Newton. If I go back and look at Newton's second law, replace Newtons with kilogram meters per second squared, and everything will work out. And when I crunch all these numbers, I get 1.99 times 10 to the 30th kilograms. And I double checked with a Google search, and I think it said 1.989 times 10 to the 30th kilograms, so looks good.